Chris, I'd love to hand back to you. Thanks very much.
Thanks, Matt. We're going to now kick off our first panel session of the day. And our panel session is going to be focused on the three vehicle software trends and what the industry should do about them. And I'd like to introduce our panel speakers. First, Matt Jones with Wind River Systems. Also, Rainer Lang and Dimitrios Stavrianos from Robert Bosch. And Tiro Salmonen from Open Synergy. Welcome, gentlemen. It's a pleasure to have you this morning. And we're going to start with Matt Jones, who's going to give a little bit of an overview on artificial intelligence as our first trend.
Thanks, Chris. So I'm going to talk only for a few minutes on artificial intelligence and machine learning and how it's having effect in a multitude of industries, including automotive. But most importantly, what do we need within automotive to really go to that next level of artificial intelligence? How can we enable all of our developers to use it more easily? And there we go. So for many years in the US, the DoD, the Department of Defense, has had a strategic focus for military aircraft on AI. If you look at many of the different open source projects for collecting data, they've had huge contributions for alliances like DARPA and others. And you see the same in Europe and across the globe. And ultimately, they have this challenge within the defense sector that they now have to have more AI to effectively offset some of their challenges. But they're not keeping that a secret. They're not keeping that to themselves. And this is where we're seeing AI come out of military aviation into the car, into the cockpit. Very, very similar libraries, very similar algorithms, multi-use algorithms. And we're even seeing the same piece going into factory robotics, which you might have in your marketplace on your OEM line. But what is AI and why is it so important? Well, AI is a technique that enables computers to mimic human intelligence. That's actually incredibly hard, especially on an embedded system with constrained processing power, constrained memory, constrained storage, and in reality, constrained connectivity. A subset of AI is machine learning. And these are really the statistical techniques that enables machines to improve at tasks that they experience. And then finally, you have this deep learning, which is another subset of machine learning that's composed of algorithms that permit software to train itself to perform tasks. Now, what we're really seeing in a lot of these factory robots, a lot of these military aircraft, a lot of these aerospace systems, it's not artificial intelligence to the nth degree. It's not relearning models in that embedded system. It's effectively a cadence where you have algorithms that are created through deep learning, machine learning, artificial intelligence in the cloud. Those algorithms are then put into the embedded domains where they generate data. And those data from the various different vehicles, the different systems that they have, are returned to the cloud in order to improve those algorithms. But what does this mean if you want to effectively train artificial intelligence models for the next generation of automotive in any sense? Well, firstly, if you think about those artificial intelligence models, they are not entirely safety critical. Those algorithms are generally designed to run on a Linux first approach. Linux, obviously, Geneva has been working with for many, many years. And this means that at this point in time, we're seeing this split of guest OSs like Android for infotainment and others, Linux for many of these non-safety critical applications, as well as safety critical real-time operating systems for that limited subset of the features that can be proven safe for AI-powered systems. Think of that RTOS of the typical braking system, control systems that you would have in a vehicle, but think about the Linux domain more as robotizing the driver. And for that reason as well, we see a lot of people moving to these standardized frameworks. I'm really talking about ROS, robotic operating system, which you find a lot in industrial. Within automotive, there's AUTOSAR adaptive, and there's other more proprietary methods. Again, all of these different frameworks are designed to run across real-time operating systems and Linux, all designed to data log, you see at the bottom, and machine learn and simulate to get that data back so you can better train your models. But what does this mean from an automotive perspective? Well, one, if we're going to update models, update algorithms, we need new ways of deploying to targets. And in reality, your system is now not all of the ECUs in the vehicle, but it's the cloud that's training the models, that's holding the software that can be sent to the vehicle. And as we mentioned before, there's this typical iterative loop where you train a model with data in the cloud, you update the system in the embedded domain or the simulation, you gain more data. Not only is this critical for OTA, but it's critical to have systems that can effectively consistently update the device and enable all of the developers to really iterate around that data. And this is why within the DevSecOps domain, in the DoD, in aerospace and defense, in industrial, it's becoming more and more tightly coupled. And DevSecOps, as you would know, it's CI/CD, but really securing the lifecycle of the software, as well as securing what the output is. I get to talk to a lot of different industries these days, not just automotive as I have in the past. And even the DoD, the US Air Force, one of the slowest organizations known in the past, has embraced this idea of centralized software factories for all of their different vendors. In automotive sense, it would be centralized software factories that even OEMs could share, even tier ones and software partners could input into, where you have that history of all of the different pieces of software that go into these vehicles, especially critical with vehicle-to-vehicle communication, where different makes and models could go across. And leading on from Geneva's cybersecurity approach, how you can do your best to secure the output of these systems. Effectively, that DevOps powers all of the different applications you run in the cloud or on that embedded environment. But let's think about how this applies to automotive. And in reality, Tesla's already doing it. Tesla sells a car. It gets the data back instantaneously. Every developer on the desk can see those different pieces of anonymized data. From that, the developers at the desks simulate, create new software that are pushed out in the overnight updates to the product, closing that feedback loop, allowing the next range of data to be collected. So with that, I'd love to pass on back to Chris, ready for the second presentation.
Thank you, Matt. I'd now like to welcome Rainer Lang and Dimitra Stavrianos from Robert Bosch, who are going to give an overview on the digital twin trend.
Well, you heard already from Matt that it's important to close the loop. And with our first slide that you hopefully see just now, you will see that we're working exactly on closing this kind of loop. If possible, would you please go forward to the next slide? So what you will see just now is a picture of the integrated lifecycle, and I think that fits very well to the already shown slides by Matt, which is closing the loop more from a development point of view. And I hope that this slide will show somehow now. Dimitros, can you take over?
I cannot change the slide.
Okay, we've got the same problem then again. Okay, no. I can do it, so probably it's working. What you see here is our slide of the integrated lifecycle, starting with the as engineering view and as the produced view and the as operated view. And what we're doing currently and what we work on is exactly integrating these views to a common value stream towards the car and getting this integrated. So also we are talking about closing the loop and getting forward and getting this data integrated in the form of a digital twin for cars, but also integrated with all the data out of engineering and as produced. As you probably know, is we're working on open standards, and we do believe that one of the things that's highly needed to do so are open standards. It's not possible to actually do this proprietary. We will need a good approach to actually make this an open standard and go forward with it. One example of such an open standard that we're supporting is the open manufacturing platform, this time as we would say for manufacturing or as manufactured in our terms. But on the other hand side, it shows exactly to what we are committed. We were using open standards, we work with partners, and we do believe that it's not possible to do this without partners, as we cannot see a proprietary approach working here. So what we're trying to do and what we would like to do with you is we're currently working on open aspect models, which is not something completely new, but we're actually trying to do there something a bit different. It's based to some extent already on Shinibi approaches, and we're combining that at this point in time with open ontology layers to get what we would call the digital twin second generation. And we believe that this digital twin second generation in the combination of aspect models and open ontology will allow us to be far more innovative and at the same time have more learnings about the data and go forward with different ways and means. And by the end of the day, it will also be a part of making AI easier by doing so. And how we do this from a vehicle point of view will now be shown by Dimitrios.
So, hello, you see the slide shows the interaction beyond production. This means that it shows what happened in the development phase and in the operational phase after you have the serial release. You see the digital twin is here presented as a line 8. It's behind the process. On the left side in purple, you see the pre-SOP or the development phase, which is already known. I think here you have, first of all, the requirement specification, then you have the development phase, next you have the test phase, and finally you have a release. If the technical maturity or the requirements not met the specification, then you go in additional cycles. This means that you will make an analysis and you make a requirements or specification correction and make the next sample in the development phase, which goes on with test until the release. When you achieve at this time, you get all the time you have the digital twin supporting you in the development phase, because you see also that there's the car which sent all the time data to the digital twin. And this is done in the pre-SOP phase by test benches or test vehicles. When you go in the operational phase, in the serial phase is the blue circle here, the digital twin continues to get the data between the operation. You observe this data, you make analysis of the data, and you can do now with the digital twins optimizations on hardware, on software. Then you continue with the next release, then you operate again. It's very close to the DevOps cycle here. And what we do exactly with the semantic stack is here, we have on all these data pods, which the semantic stack combines the data, which you can, and so you can increase the efficiency and you can make the analysis of the whole life cycle. This means from the operation till to over the development till to manufacturing. And the key fact that you have with that, if you use that, is that you can use the statistical robustness of the world of the fleets for world fitting. Vehicles are becoming in the post-SOP phase additional validation environment, and so you can optimize hard and software, but also you can customize software to increase the user experience of the driver. And what is really important is that you can speed up the software development and the innovation cycles. And last but not least, you can also make with all this topic additional digital twin-based services. But To realize that, you need a special architecture. Can you switch the slide? This architecture is shown here. We named it service architecture. You see the different layers from embedded to cloud. We have the ECU part with a microcontrol-based ECUs and sensors. We have the vehicle computer with an abstraction layer, and we have the cloud where the digital twin is hosted. If you focus now on the ECU, you see, you see that we have two topics. We have a data preprocessing and service-specific code. We choose also here to show you the pyramid due to the topic that is really important. If we want to use the data over the whole life cycle, you have to increase over each step the data value to reduce the data traffic from vehicle to cloud. And this will be done here by data preprocessing and service-specific and implementation of service-specific code. An important topic in the middle of the part is in the vehicle computer is the abstraction layer. This has the task to combine the effect chain-based algorithms of the embedded layer with the data-based algorithms on the vehicle layer. With these topics, you can now go to have a continuous X framework between, today clouds are used as an cloud extension, and in the future you will have to get the maximum efficiency out of digital twin. You will need a continuous X framework, and this will be done by the cloud and the vehicle, which is also necessary to have to implement a basic foreign So this is important to implement it, because you need this continuous X framework to can merge the cloud with a vehicle computer. Thank you. Back to you.
Thank you, Rainer. Thank you, Dimitrios. I'd like to now welcome our third.
Hardware architecture where we are, and then discuss a bit at what we can do with more software-oriented approach. So here you can see the on top left, you can see the current architecture that we have in the car. So it's full of different ECUs. So we can have up to 100, maybe some more in some cars. They are connected, but they are very distributed. So that's where we are today, but where we are going is more centralized, consolidated architecture, where you basically have more computing power in computers, central computers, or domain controllers, or zone controllers, whatever you want to call them, which are then basically connected to the controllers near. And concentrating on the some functionalities in various parts of the car. So this transition is something that has been discussed for a while. It has been ongoing, but it hasn't like moved so fast yet. But pretty much everybody sees that we are moving towards something like this. It probably will take something like 10 years, so it's not happening very fast. But it's ongoing, and we see some consolidation in the area of cockpit, for example, at the moment. But it's kind of important that we still see in the industry a lot from the hardware point of view, and that limits us in a certain way. So instead of having 100 boxes, we might have, let's say, a bit smaller number of boxes, but we are still thinking from the hardware point of view, and we are basically taking hardware, assembling it, and then making software on top of it. But what we could do differently, if I can change my screen, yes. So what we can do differently is that if we look the problem from the software point of view, so we don't care so much about the hardware, we look on the software that we want to build. And we basically look around a bit and see what the other industries are doing. So there was examples from cloud in previous talks. If you look the architecture of the cloud and how the software is forming it, we can learn a lot of things. So there's this term called software-defined architecture. That's very much coming from the cloud world. But that's a good like buzzword or term in a way that it forces us to think differently and allows us to look from the functionality point of view and software point of view and not concentrate on the hardware and not use the hardware as a starting point for the design decisions and other decisions. What we can adopt from the cloud world is the very basic architecture that you can see here in the right. So you can separate the hardware from the software. So we have some applications. This can be full operating systems or smaller stacks. So they are pretty independent. They're running on top of some standard APIs. We use virtualization to make this available. Different capabilities to be available. And then we have the hardware in the below. So this allows us to basically separate the applications from the actual hardware. So what we can do is that we can provide the capabilities, meaning data, storage, compute, networking, graphics, sensors, whatever is needed by the applications in virtualized way through these node-bound APIs. So they're basically APIs that can be used by any application or operating system or service. And then you don't need to care about the hardware so much anymore. You can just care about the capabilities that are available in the environment. And it basically frees us to build the hardware in different ways. And it doesn't lock us to any particular system. So it can be like one giant computer, or it can be more distributed model. You don't need to care about it if you think from the software point of view. So you basically just care that your application or operating system or service or whatever it is has certain capabilities available, and it can have them when they are needed. So that's what the software-defined architecture aims for, and where it has worked very well in the cloud space. And we can basically use similar kind of like ways to build the software and consolidate the software for the cars. So we can pretty much build the same system, and there's already some work on this in Genevieve context also in the hypervisor projects, where we are basically defining these node-bound APIs, how the operating systems and the services and applications running there actually use the hardware. In device virtualization, for example. So that's what we can do. What we will need is this orchestration part. So it's basically management of the whole system, so that you can do software updates that was discussed already before by Matt, for example. You can make configuration changes, and you can basically also monitor the system in multiple ways. So that's a crucial component in this kind of architecture. And then you have the hardware. And now what is beautiful in this kind of way of thinking is that the hardware can be built in the different ways. You can like plug and play hardware as long as you basically implement this southbound API here. It allows the virtualization layer to expose these services or capabilities to the application layer and operating system layer, which is basically using then these standardized node-bound APIs. So this is what we could try and what we should try to do in automotive also. So learn from the cloud, adopt the concepts that are seen working there, and use them in the context of the car and the software that is running in the car. So that's brings us great benefits on the consolidation. We don't need to care about what's underlying hardware is. We just care about the APIs and the ways that the applications are and operating system are using those APIs. And then we can deploy these systems in different ways. And we can also like have a lot of flexibility on the actual system. So it's not that you take one SoC and you build something for it. you basically take some capabilities and you build enough of it, and then you run your software in different kind of end systems easily. And this is what the software-defined architecture can bring to the picture. If you think like this, then you can basically turn around the system inside the car, and you can utilize existing technologies pretty freely. Of course, we have some particularities in the car that we need to take care of, but there's a lot that we can learn and take from the Cloudflare in this kind of consolidation phase. Okay, so what would we gain from this? So basically, this kind of environment can be more standardized. So basically, we have a lot of portability. There's no lock-in. So you can switch hardware, you can switch software, use different vendors, use open source. So it gives us a lot of like flexibility and portability, and in the end, of course, then lot less cost in the picture. It gives a lot more freedom to the hardware design and selection. So you are not tied to anything particular. You can have much more flexibility on the hardware side. You can buy certain things from certain vendors, certain other things from certain other vendors. You are not locked on it. If you want, you can, but you don't have to be if you think software first. And then this kind of environment, when you think what your software needs to do and what it needs to run, it's rather easy to standardize, and also easy from that angle that okay, a lot of it has been done already. So it's basically very fitting to the organizations like Genevieve and what Genevieve tries to achieve. All right, that's all from my side. So back to Chris, to you. Thank you.
Thank you, Tero. We are now going to move into our Q&A part of the session. How do you see that playing a role in autonomous transportation, fleet management, things of that nature going forward as well? I don't know, Dimitrios, if you want to take that
I
first,
think
or Ryan.
Dimitrios is the better one there.
Okay.
Okay, sure.
I think it will play a really big role there. And the reason for that is, as shown, that you can support also services there. And with these services, you can make value add for the customers. And therefore, I'm sure that the digital twins will support there a lot. And also I mentioned the topic is you will need this service architecture for the safe handling of data configuration and code. And if you have that, then it will be easy and you can create value add with the digital twins there.
Fantastic. Tero, question for you. What do you see as the priority vehicle functions for moving to a software-defined architecture? And how will this be addressed over the next, say, 5 to 10 years?
Yeah, I think in the beginning, it's probably going to be more like the cockpit features. So basically, because the consolidation is happening there already. So there's so many functionalities inside the cockpit beyond the IVI system and the cluster. You have DMS systems, you have cameras here and there, and all of this is probably going to be consolidated in coming, let's say, next 5 years. And there's a huge opportunity to use software-defined architecture in this kind of setups. Then after that, we probably start adding the connectivity part and some processing of the data, and then you can move further from that. But in the beginning, I see that it's going to happen in the cockpit side. So it's kind of extending the IVI system with other functions and consolidating these. And then it's a great place to actually use something like software-defined architecture.
And Tero, so if you looked at the next, say, 5 or 10 years, what do you see as realistic deliverables or milestones achieved over that period of time to the cockpit or to other advancements that you're working on?
Yeah, it really depends on the computing power that is available. So pretty much we can consolidate a lot if we want. if we just have a computing power enough available and we have certain capabilities, we will need certain capabilities still to be available in the field. So there's certain technologies that are coming, and then it basically allows system to SoC level to have cache coherence, for example. So when those are available, then we have a lot of opportunity, and this will happen in 3 to 5 years from technology point of view. Then of course we need to build the frameworks, and we need to build different things, take safety and security and all of these kind of things in the card. But technology wise, I would say in 3 to 5 years it can be there.
And related, I'm glad you bring up safety in some of these elements. Rainer, you and Dimitrios, in your discussion, talked a little bit about over-the-air software capabilities and the ability to provide real-time updates that impact operations and safety. Can you talk a little bit about what we can continue to see moving forward as that technology continues to advance, and what kind of added benefits will play from a safety and operations point of view?
I think, yeah, I will answer that, Rainer. Okay. I think you will have a lot of value-add services also in the safety there. I think the biggest issue is what you have to handle is the security over the air and the data traffic. Because if we start to share a lot of data of the vehicles, then we will have in the future a data tsunami, something like that. Therefore, we need to make smart data instead of big data.
Okay.
And I would like to add that with the semantic and ontology approach, we can make out of big data, smart data. And that's what we're currently aiming and concentrating on, of using that kind of technology to make it better understandable what's happening to the data. And we also consider using that then towards the car.
Fantastic. We have a question from the audience I want to pose. This is related to the digital twin technology. Does the digital twin concept include working simulation of all the working vehicles, and how would digital twins model how the mechanical systems respond to the software interaction? And I'm not sure, Dimitrios or Rainer, which of you would like to take that?
That's a little bit more in my direction and my part of the game.
Sure.
We're currently looking on how we can get mechanical models basically, and also software integrated into the digital twin. And we're currently working on concepts how we can do that in the similar way. And we have a lot of research guys helping us with that. And I believe that we will make in the next year also a huge step forward in getting also mechanical simulations and other things directly being part of a digital twin and helping us to make better decisions about what's going on in the field and what's happening in combination then also with manufacturing.
And Matt, you brought up an interesting point in your presentation, talking about what advancements have been happening in military applications and how that could be influencing what we're seeing in the commercial markets. Can you talk a little bit about what things we might be seeing on the horizon that perhaps the military has been doing on AI, autonomy, and other related topics that you think is going to be perhaps critical to pushing the commercial markets even farther forward?
Yeah, and I think there's a number. If we start with this concept of moving big data to smart data, if we look at topics that Geneva are working on at the moment with others, if you think of the NSA's project that they released under the Apache Foundation called NiFi, sponsored by Cloudera and others now, this is very much about being able to steer, right, if this, then that type rules within the cloud and then distribute those to Minify and others on the edge. So we're already seeing this massive data processing to not have to collect all the data in the field in real life scenarios in order to get that multiplicative effect. We think of other types. There's a huge amount of sponsorship going into algorithms within the military domains that start to solve some of the problems of moving the positions of the sensors. So if you think of two different camera systems, one high up on an SUV, one low down on a sports car, they see the world from different points of view. If you move the radar, the LiDAR, and the cameras to different locations, again, they see the world from different points of view. At the moment, some of the autonomous vehicle intelligence systems in the sensor fusion, the perception stacks, need to be retrained if you have significant changes. But if you take a different view of the world, one where you understand more about 3D space, where you take a time-based situational awareness, where you drive past a tree, you get to build up a picture of that tree. Very hard to do, but once you've done it a number of times, as you would in the military or these other situations, then you can start to be able to train models for camera placement much more easily. And I'm very much hoping that comes to automotive. But the big difference I see between the way the military, aerospace and defense, and even industrial, a lot of the big companies like Amazon, Microsoft, Google look at this. Amazon, Microsoft, and Google are not waiting for the silicon to be able to be affordable in an automotive context before they start the research. So I see them effectively researching how they'll be able to do artificial intelligence on the edge, on the device now. Whereas in automotive, not all companies, but certainly some of the companies are still waiting for the silicon to be automotive qualified or with their roadmap. And then they start their research, which does tend to lead to this longer tail within automotive than in some of the other areas. Automotive is almost limited, self-limited by what's available on the silicon, whereas other industries tend to be proving the algorithms work on unaffordable silicon and driving the cost down. And that's not entirely true, but it's an interesting topic for debate.
And Matt, to that point, do you find that some of the sensor technology and things that are being used in the military for predictive maintenance and fleet and things of that nature, that you're going to see more of that kind of advancement into the commercial markets and happening at a faster pace?
I think so. And if you think of the military, there's 1, 2, 3 governmental big sponsors of it. So there's much more of an incentive to work together. So you get the Boeings, the Rayothans, the Lockheed Martins, all working together from the very start because they're paid to do so. And even though they're kind of OEMs, they produce the F-35 in their own right, they produce the different vehicles in their own right. They're all paid by that same government entity, which is a very different makeup than you see in automotive, where BMW competes with Genesis or any of these other makes and models of vehicles. But they're all having to work on that same platform, not necessarily what we see within automotive. That does give them an advantage.
That brings up a great point. And I was with representatives from around the world. How would you, and maybe for Reiner and Dimitrios and Tero, how would you describe the information sharing that's happening around the data twin process, around this architecture across OEMs, tier 1s, and across international borders? Are you seeing more of a collaboration and a willingness to try to share insights, or is it more of a proprietary type of structure that you're seeing going forward?
I think it's changing at the moment, because what we see is that, I would say we understand that if they want to, the OEMs want to have a vertical integration, then they have to open to work with us, and then we support them with the necessary data to get also this vertical integration of the components. And I see that here is a change in front of us.
I would agree to that completely, and we see already first OEMs basically learning that they need to get in a partnership about using data, and that needs somehow trust and reliability, of course, but we see the first movements there going in a direction to be open on using data together. And I think that's the right way, because by separating everything, trying to do everything by themselves, it's not going to work for a long time that way. That's exactly the reason why we showed open ontologies and open standards, because this data needs to be exchanged in a way that we can understand it and that we can use it from the beginning. And I think that's key for the next, I would say, 5 to 10 years, from my point of view, in this environment.
And if you take a look also to the other tiers, if you want to have new services or new value add information, then also the tiers can work together to open new tasks there and create new value or new services for the customers.
And that's a good point, Dimitrios. So if I'm an automotive customer, what exciting things can I expect to see in the next 24, 36 months as a result of this shared collaboration, result of this innovation on AI, on the digital twin side, on the architecture side? what tangible benefits might I see in the finished product of the vehicle?
Oh, I think that, yeah, we have interesting cooperations there, but I think it's a little too early to speak about them. But I would say the very important topic is that we can create value-add services for the final customer together, and this can be done with the tiers, but also with the OEMs. And this is, I think, the important topic. If we work together, we can make more services for the customers together.
I have to ask this question because obviously we're all living in an extraordinary year that nobody ever predicted. How has this year changed how you're going about your work? The benefits, the unexpected surprises, things that you've collectively learned as a result of our changed working environment. I'm just curious, how that's played out for all of you.
Yeah, I think yeah, the world is changing, and it's very interesting to see how you can now work with also with new companies with innovation ideas, which you can say, okay, we can do it together and scale our innovation. And therefore, I think it was in the past was not possible, but now I think we have a bright future.
Reiner, Matt,
well,
any thoughts you have on this?
I would say in my environment, it has taken out a hell of a lot of emotions and makes things more factual, that we're working really to the point of it. And it's also in our outside perspective, getting easier to talk to people and trying to have real partnerships was easier this year than it was ever before. The interesting part currently is we even make that happen with tools like Zoom or Teams or things like that. Nevertheless, we still see the benefit of sometimes meeting people in person. So I would say it has changed quite dramatically. We're still progressing comparably well, I would say. Nevertheless, it's sometimes important to meet people in person.
I'd agree with that. I think throughout this COVID incident, Zoom in reality has been a great leveler. So previously, if you had 6 people in a conference room and 3 people remote, the 3 people remote on Zoom would feel like second-class citizens. At this point, we're doing an entire conference on Zoom. You can meet 4 or 5 different companies and everybody is just another window in Zoom. I think that this has really helped collaboration, especially in automotive. I worry in a way. I think people almost need training when we do start to go back into the offices to remind people, when you're sat there with 4 others in a conference room, just look after the people that are at the end of the conference room line on the Zoom piece. It's definitely hasn't hurt business and it hasn't hurt collaboration from my perspective.
That's good feedback. Just a question for all of you. This has been obviously an extraordinary year. As we move toward 2021, what can we expect from the industry and across your practice areas and the work that you're doing? What lies ahead? I don't know who wants to take that first.
Yeah, that also probably the speed of the change will accelerate because you have to. So you have to run faster because there's less available. So there's a discontinuity point clearly because of COVID. So the innovation probably will jump next year and years after that. So we will move much faster pace in automotive. So we had these technological changes. We have the electrification, and we have other things. And now we have COVID also. So all of these together, they will accelerate heavily the change in our industry especially.
I think 2021 is going to be the year where, as well as talking about the technologies we build into the vehicles, how we accelerate that, it's almost coming off the back of COVID. It's how we collaboratively develop. So in the presentations, you've seen that cycle need to develop, deploy, get the data as rapidly as possible. I think there's going to be a refocus more and more on the tooling and the collaboration tooling, the DevSecOps environment, on how you can make your limited software resources more and more productive. Why does it take 2.5 hours to do a Linux build? Why doesn't it take 5 minutes? Why can't I get all of the data of all the traces back to my developer's desk? Why am I still passing USB sticks or relying on email traces? I think there's an awful lot that we can do to make software within automotive and all of the ecosystem more productive to get to that next generation of software faster?
Well, from our point of view, it will be a very data-driven year where we concentrate on learning more out of data, using data to our benefit, and going forward in that kind of data-driven life cycle.
And I would like also to add there, I think the vehicle will change to a software and data defined system. This is the first topic. And we will increase or speed up with the innovation cycles. I think we will also see that. And what we see also for the future is that I would say the big bang development doesn't work. I think you need more corporations there and support to know exactly what you have to do. Because in the past, we have the procedure that we develop something with 3, 4, 10 sample phase or software releases, and at the end we bring it to the market. I think this doesn't work in the future, and we have to collaborate there better.
That's a great point. Well, gentlemen, I want to thank all of you for your time and input to today's panel discussion. This has been a great chat. Any questions we have offline, we'll try to direct those to you after the session. In the meantime, we are going to take a small break, and we're going to be presenting a video from both Genesis, Cloudera, and Geotap. And we'll be back on here. Our next session will be discussing Google Automotive Impact Statement, and look forward to having that discussion resume shortly. So thank you all, and we'll be back with you shortly.
Thank you, Chris.
Thank you.